In this section, we have two objectives. We want to identify the common ratio of a geometric sequence and find the given term and the sum of the first n terms. And B, find the sum of an infinite geometric series if it exists. So a sequence is geometric if each term is the product of the common ratio r and the previous term. That is, a sub n plus 1 is equal to r times a sub n. Solving that for r, we get that r is equal to a sub n plus 1 divided by a sub n. So to find the common ratio, it says we need to divide a term by the term that came before it in the sequence. So in example 1, it says find the common ratio. So in this example, we have a1, a2, and a3. So then our common ratio, r, would be a2 divided by a1, so 45 over 15, which would equal to 3. And if we checked again with a3 divided by a2, we would have 135 divided by 45, which is also 3. And it's worth noting that what we did to get to the next term each time was multiply by 3, which is the same thing we got for our common ratio. All right. So the general term of a geometric sequence is given by a sub n is equal to a1 times r to the n minus 1. So in order to find the general term of a geometric sequence, we need to know the first term, and we need to know the common ratio, r. So in this example, we want to find the general term. So once again, we have our a1, a2, a3, and so forth. So to find r, we divide a2 by a1. So we have negative 1/2 divided by 4. And we can make 4 a fraction by putting it over 1. If we have a fraction divided by a fraction, that's negative 1/2 times 1 over 4, which would give us negative 1/8. We can also do that fractional arithmetic on our calculator if we wish. So remember, we go alpha y equals to get a fraction. And then you can put another fraction in your fraction. So we could do the negative 1/2 is the numerator of the fraction, and then just divide by 4. And we'll see that our calculator agrees with what we got of negative 1/8. So then to use our formula here, we just need to know a1, which we already do. So a sub n is equal to a1, and our a1 up here is 4. So we have 4 times our common ratio r, which is negative 1/8, raised to the n minus 1. And that would generate our sequence. So let's just verify that that's indeed correct. So on our calculator, we press y equals, and we can type this in. So we go 4 parenthesis, grab our fraction, negative 1 over 8, and we're going to raise that to the x take away 1. And if I go second table, it will generate a table of values for me. So when I put in 1, we get 4. And if I put in 2, we get negative 1/2. And so forth. So we get the following input-output pair. And indeed, we notice it exactly matches, at least for the first ones that we can see for a bit, what we had in our list over here. All right. So now it's your turn. Please go ahead and find the general term of this sequence. So we look over here and we see that our first term, a1, is going to be 3, and our r is going to be a2 divided by a1, which is 6 divided by 3 gives us 2. So then a sub n is equal to a1, 3 times 2 raised to the n minus 1. And that would be the general term of this geometric sequence. Let's transition. We want to talk a little bit about geometric series. So in a previous video, we talked about wanting to try to add up an infinite geometric series at some point. And we're going to get there a little bit later in this video, but for right now, let's take a look at this and see what we have. So if I look at 1/2, if this square right here is a square with side length 1, then its area is going to be 1 times 1, which is 1. So if I shade half of this, let's do the bottom half, that would represent the first term in our series. Because if this has area 1, then half of it has area 1. And we're going to have that in all of these squares. So then, if we keep on going as we do this, we now want to get to our next term, which is a quarter. So a half plus a quarter, well, a quarter is half of a half. So if I shade that in for each of these, so my first partial sum, so s sub 1 is equal to a half. S sub 2, a half plus a quarter is 3/4. And we get to our next one, we add an eighth, so that's half of a half of a half, so that's one of these little triangles. So then here I would have 7/8 of that filled in. So 7/8. And I'm running out of colors, so we'll do our last one right here. And that's going to give us 1/16. So our s sub 4 is going to be 15/16. Well, a couple of observations. We know that the area of this entire square is 1. And if I keep up this regimen of dividing it in half and filling in half of it, divide what's left in half and fill that in, am I ever going to fill up this entire square? Well, for any finite number, no, that's not true. So what do we know a half plus a fourth plus an eighth plus a 16th plus 1/32 on forever is always going to be less than or equal to? Well, we know that it has to be less than or equal to 1 because it fits inside a square that has area 1. All right, well, let's analyze our sequence of partial sums. So we have a half, we have 3/4, we have 7/8, and we have 15/16. So we have a pattern where our denominator is doubling every time, and our numerator is always one less. So our next one, we double 16, we get 32, 31 in the top. We double 32, we get 64, 63. And if we keep going on forever and ever and ever, we might notice that our pattern is s sub n is equal to 2 to the n minus 1 all over 2 to the n, because the numerator is always one less than the bottom when we're doubling it each time. By termwise division, that's the same as 2n divided by 2n minus 1 over 2n, which is 1 minus 1 over 2 to the n. Well, as n gets bigger and bigger and bigger, 2 to the n is going to get bigger and bigger and bigger, and 1 divided by really, really big is going to get closer and closer to 0. So it appears that this reinforces what we saw up here in this picture, that the area is going to get closer and closer to 1. All right, so eventually we want to answer that question, but we're going to put this on the back burner for a second. And we want to talk about finding the sum of a finite geometric series. So if we do that, we're going to have S sub n is equal to A plus A1R plus A1R squared plus, and we do that all the way out, A1R to the n minus 2 plus A1R to the n minus 1. So the first n terms would start when we have the exponent n minus 1. So to find the sum of this, we're going to do a trick similar to, but not the same as, what we did with Gauss. So imagine if I multiply both sides of this equation by r, and that would give me r times s sub n. Well, that's going to multiply every term on the right by r. So a times r is going to give me a1r, and a1r times r is going to be a1r squared. So it's going to increase all of my exponents by 1. But when I increase a1r to the n minus 1, I'm just going to get a1rn. So now, if I subtract these two equations from each other, I'm going to get Sn minus r times Sn. And then on the right-hand side, all of the terms except for the very first one and the very last one are now equal but opposite. So they all reduce out and add up to 0, and I get a1 minus a1 r to the n. So now if I solve this equation for Sn, I factor out my common Sn on the left, so that leaves me Sn times 1 minus r. Factoring out an a1 on the right, I get 1 minus r to the n, and I divide by 1 minus r, and I divide by 1 minus r, and that gives me that S sub n, or the sum of the first n terms of a geometric series, is equal to a1 times 1 minus r to the n, all divided by 1 minus r. So that gives us the following. So now we wish to find the sum of 2 plus 6 plus 18 plus ... all the way out to 1458. So the first thing we're going to need to do is we need to identify our a1, and that's easy. So what's our first term in our sequence? Well, that's going to be 2. So a1 is 2, and then we need to find r. Well, r is our second term divided by our first term, so 6 divided by 2 gives us 3. The last thing we need to use this formula is n. But with a1 and r, I can find the general term of the sequence. So a sub n is a1 times r to the n minus 1, which is 2 times 3 to the n minus 1. And now I need to solve a sub n is equal to 1458. So that gives me 2 times 3 to the n minus 1 is equal to 1458. So solving this exponential equation, I divide by 2, I divide by 2, and I get 3 to the n minus 1 is equal to 1458 divided by 2, giving me 729. So then to undo an exponential base 3, I use a logarithm with a base of 3. So then on the right-hand side, the logarithm and the exponential reduce out, and I just get n minus 1 is equal to, and then if you don't know this off the top of your head, that's fine. You go alpha window, and you choose choice number 5 for log base. So the log base 3 of 729 is going to be 6. So then we add 1, and we add 1, and we get n is equal to 7. So now we know n is 7, and we have a1, and we have r. So s sub 7 is equal to a1, which is 2, times 1 minus r to the n. Our r is 3, and our n is 7, all over 1 minus r. We can put that into our calculator. And we get 2 times 1 minus 3 to the 7th, all over 1 take away 3, and we get 2,186. It's also worth noting, since we know what a sub n is, we could use sigma notation on our calculator. So if we did that, and we start with n equal to 1, and we go to n equals 7, and we wish to sum up 2 times 3 raised to the n minus 1, and we press enter, we get the same thing. So one thing we do have to be careful with when using our TI-84 to do these sums is when we press our alpha window key to get our sigma notation, it's going to insert these parentheses right here for us. The entire general term has to go inside these parentheses. If you try to use those parentheses, for example, if you tried to type it like this, you're going to end up with the wrong answer if you go n equals 1 to 7 of 2 times 3, and then if you try to use those parentheses, n minus 1, your calculator is not going to object, but it's not going to give you the answer you think you're going to get. So everything has to go inside those parentheses. Otherwise, it's not iterating the n inside that loop, it's using it elsewhere. So just be careful. The entire general term has to go inside here. So the general term must be inside. All right. So now we want to talk about, well, what is the sum of an infinite geometric series? So to help us with that, we need to break this down into two different cases. And those two cases are the following. If we have the absolute value of r is less than 1, or we have the absolute value of r is bigger than 1. So the question we need to answer is, well, what is r to the n as n goes to infinity? So if we pick any number in absolute value that's less than 1, I'm going to pick 1/2, but it works with no matter what you pick. Then we wish to calculate r to the n. So in this case, r to the n would be 1/2 to the n. So we grab our calculator. Let's clear this out, and we're going to go get our fraction 1/2 to the x. And now if I go alpha trace, choose y1, well, let's see what happens as n gets really, really big. So if we put in 10, we get 1 over 1024. If we put in 100, we get 7.88 times, and then we've got this e to the negative 31. So remember, that represents scientific notation. So that says I need to move my decimal 31 places to the left. So that's going to make that number pretty small. Let's do one more. If I go y to the 1000th power, something very interesting happens. What does my calculator tell me 1/2 raised to the 1000th power is? Well, my calculator seems to think it's 0, but is that true? Well, 1/2 is a positive number, so what's a positive times a positive always? Positive. And if we keep multiplying a positive by a positive, we always get a positive. Well, what happened here is this number got so small, remember we already had to move the decimal 31 places to the left, that finally our calculator ran out of memory on the small side, so it just rounded this to 0. The bad thing is our calculator didn't tell us that, so that could be a little bit problematic. But now our conclusion then is, well, so what happens to r to the n as r gets really, or as n gets really, really big? Well, as n goes to infinity, r sub n is going to get close to 0. Okay, so that's our first case. Now, same question, but this time let's pick r equals to 2. So I go back into my y equals and I put 2 to the x. And this time, if I go and do the same thing, alpha trace, and go y of 100, we get this. And if I go y to the 1000, I get this. And this time it finally gives me an error, and it says error overflow. So the same problem happened as what happened in the previous one, but at least this time my calculator told me that it ran out of memory because we overflowed the amount of memory the calculator had available to do that computation. So it seems here, when the absolute value of r is bigger than 1, as n goes to infinity, r sub n also goes to infinity. So now, if we take a look at our formula, we have s sub n is equal to a1 times 1 minus r to the n all over 1 minus r. And we know that r cannot be 1, because if I plug r in to this formula, we would divide by 1 minus 1, which is 0, which is undefined. So if we take the limit, we let n go to infinity, we're going to have the following. So then we would have s infinity is equal to a1 times 1 minus r to the n, and then r to the n had two possibilities. So if the absolute value of r is less than 1, it goes to 0, otherwise it goes to infinity. So if we assume that the absolute value of r is less than 1, then r sub n is going to go to, or r to the n is going to go to 0 all over 1 minus r. So we simplify that up a bit, and we get s infinity is equal, well, 1 minus 0 is 0, times a1 is a1, so we get a1 all over 1 minus r. So this gives us the formula for the sum of an infinite geometric series. So one thing we have to take note of is when we got our formula here, we had this 0 that we replaced r to the n with. Right here, this only works if r is less than 1 in absolute value. So we notice down here that if r is greater than or equal to 1, we say the series diverges, or the sum doesn't exist. So for the infinite geometric series to exist, our common ratio r has to be less than 1 in absolute value. All right, so now we're finally ready to find the sum of 1 plus a fourth plus an eighth plus a 16th. So if we go back up here, that's what we were looking at in this picture. So based on what we did here, what did we guess we think this is going to get close to? Well, 1. So let's check and see if that's true. So we want to use our formula for the sum of an infinite geometric series. So we only need to know the first term and our common ratio. So the first term, a1, is going to be a half, and our common ratio r is going to be 1/4 divided by 1/2. So 1/4 multiplied by the reciprocal of 1/2 is 2/1, which gives us 2/4, which reduces to 1/2. So then S infinity for this is 1/2 divided by 1 minus 1/2, which is 1/2 divided by 1/2, and anything divided by itself is 1. So the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 on forever does indeed equal to 1. All right, so the next one is a U try for you. So let's go ahead and find the sum of this geometric series. So once again, to use the formula, the two things we need to know are a1 and r. So a1 is equal to 5, and r is going to be 10/3 divided by 5. So writing 5 as a fraction, we write it over 1, so we have 10/3 times its reciprocal, which is 1/5. Reducing these, 5 goes into 10 twice. 2 times 1 is 2/3. So our common ratio r is 2/3, and it's worth noting the absolute value of 2/3 is less than 1, so the series converges. Remember, if r would have been bigger than 1 or equal to 1 in absolute value, the series would have diverged. So now S infinity is equal to a1, which is 5, divided by 1 minus r, and our r is 2/3. So we get 5 over 1 take away 2/3 gives us 1/3. So 5 as a fraction is 5/1 times the reciprocal of 1/3 is 3/1, gives us 15/1, or 15. So the series 5 plus 10/3 plus 29ths plus 40/27ths converges to the number 15. All right, so the last example is we want to find the rational number that represents the repeating decimal 0.123123123 So at first it's not entirely obvious that this is a geometric series. So if we write out 0.123123123 if I look at my block of digits that repeat, the first block of digits is 1, 2, 3. So that gives me A1 is equal to 0.123. Then the second block of digits that repeat is also 1, 2, 3. But now for A sub 2, I don't want to change the first 3 digits. So the only thing I can add to something that doesn't change it is 0. So A2 is 0.000, and then I would do 1, 2, 3. So now to get the next term, I would have a sub 3. Well, I don't want to change any of the first 6 digits, so I would need 6 zeros. So 0.0000000, finally 1, 2, 3. And then, just to be explicit, one more, a sub 4. Now I wouldn't want to change any of the first 9 digits. So I would have 9 leading zeros and then a 1, 2, 3. And if I kept doing this forever and added up A1 plus A2 plus A3 plus A4 plus on forever, then that would give me the repeating decimal 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we'll notice, as mentioned, then A1 plus A2 plus A3 plus A4 plus ... on forever equals 0.123 bar. So to sum up this series, we need to know the first term and the common ratio. Well, our first term is right here, so we know A1 is equal to 0.123, or as a fraction, 123 over 1,000, because tenths, hundredths, thousandths. Then our common ratio is going to be A2 divided by A1. So that would give us 0.000123 divided by A1, which is 0.123. And if I divide each of these, so I go 0.000123 divided by 0.123, and get my fraction. That gives me 1 over 1,000. So then S infinity is equal to A1 all over 1 minus R. So that's going to be 123 over 1,000 all over 1 minus 1 over 1,000. So getting a common denominator in the denominator, I multiply the top and the bottom of this by 1,000. So then that would give me 123 over 1,000 all over 1,000 take away 1, 999 over 1,000. So we would get 1, 2, 3 over 1,000 times 1,000 over 999. Thousands reduce out, and we get 1, 2, 3 over 999. And each of those is divisible by 3. So we reduce, and we get 41 over 333. So that's going to be the repeating decimal 0.123. And if I check that on my calculator, I can go 41 divided by 333, and indeed I do get